Okay, hello everyone. Welcome to this colloquium. It's my pleasure to have Simran Arora. She's a PhD student at Stanford. She's working with Chris Ray, and she's been doing a lot of interesting work at the intersection between systems and machine learning. Today, she's going to be talking about, for instance, the Pareto frontier between efficiency and capabilities. She has worked on sub-quadratic complexity models, which achieve state-of-the-art efficiency, state-of-the-art accuracy. She has worked on techniques for automatically distilling kernel code based on just a small amount of specification of what needs to be done. So there's a whole suite of work she's done, and a lot of that is actually informed by hardware capabilities and trying to understand what should be the ML sort of architectures which should take advantage of those hardware capabilities. So with that, let me hand it over to Simran. Pleasure to have you.
Thank you. All right. Hi, everyone. Excited to be here today to talk to you about my work at the intersection of AI and systems. So first off, let me tell you a little bit about myself and where I'm anchored. So while we've made a lot of progress in achieving and unlocking new AI capabilities over the past several years, I'll just state that we've really anchored on one recipe, so training massive models on transformer architectures on NVIDIA compute, a narrow recipe. And my work is motivated by the view that this is just one of many, many possible recipes that can get us to high-quality AI. And some of these recipes can be orders of magnitude cheaper than our current status quo. There are so many interesting possibilities to consider, and we're only just beginning to understand the landscape here. And I strongly posit that new breakthroughs won't just come from the status quo that we've been after, this recipe of massive scaling, but rather through careful design at the intersection of AI and systems. So again, massive models on NVIDIA data center compute has been status quo. And for a variety of reasons, this is just a small fraction of AI's potential. So first, a basic one. This is the central geopolitical question right now, is how we can get these capabilities in AI for far, far cheaper, both in monetary cost and energy. Secondly, many applications cannot live in this regime of massive models. So since 2013, I've worked with an organization called Luma to provide educational technology to schools and developing communities in South Asia. And here the idea is, can we provide a little box? It's very much like a smart board that has educational database, textbooks, Khan Academy videos, et cetera on it. And can students go and interact with this content to bring technological educational content to a place where traditionally there isn't access to these types of resources? And there the goal is, how can we put as high quality of AI models to allow students to ask questions over this content and search over this content, but have this model be as small as possible, as high quality as possible. And this is not some fancy data center GPU. And finally, there's been a lot of talk of personalization in general in AI, but really, if any of us really thinks about it, we don't have any personalized AI right now, and I think this is a key promise of AI that we're missing out on. So for various reasons, we need to go beyond this, understand the recipes and possibilities here in AI and systems. And so by pushing on this perspective, I've been able to address important problems in computer science in the pillars of systems, hardware, and AI algorithms. This work has been cited by the Department of Homeland Security, won Best Paper by the NSA, and is used in various research, open source, and industry projects out there that I'll touch on a little bit throughout the course of this work, of this talk. There are many aspects of this that I would be really excited to tell you about, but in the interest of having one theme for the full talk, we're just going to talk about one question. How do we make language models efficient? What is the Pareto frontier between throughput efficiency and quality for language models? OK, so with that in mind, with language models these days, we can build systems in hours that used to take months of manual feature engineering and engineering time. So for instance, we can automate complex process workflows. We can have our models help us generate text given context of our repositories and abstractions and files we care about. We can have models go and analyze massive amounts of documents and messy, unstructured corpora. The core issue is that as we try to apply AI to a wide variety of these tasks, where I'm hoping many of us have this experience or are aware of this phenomenon called in-context learning, where we can pass in what we care about the model doing, information about our task, into the model's context, and it just generalizes to do these tasks without any task-specific training whatsoever. And as we try to apply this in-context learning to a wider variety of settings, the core bottleneck and a key metric has become how we can improve the throughput efficiency, or the number of tokens, amount of data that a model can process per unit time. And this is a key bottleneck in machine learning right now due to our choice of architecture, the core building block of our language models, which is something called the transformer. So this workhorse of AI is inefficient for several reasons. A transformer, or a model in general in AI, is built up of many, many layers of different operations that we care about doing. And in a transformer, two core operations are something called an MLP and something called attention. I'll focus on attention for this talk. If we pass in some input to our model, so imagine providing in a document to ChatGPT of some sequence length, for this talk, I'm going to denote that sequence length by the variable n. And we represent that information, those words to the model, in some representation dimension d. And the compute requirements for attention scale quadratically in the sequence length of the input the model is processing. And the memory requirements scale linearly in the amount of data the model is processing. Hardware has limited resources, limited memory, limited compute, so this presents a major throughput efficiency bottleneck. Our question is, can we replace these operations? Can we replace attention with more efficient alternatives, and how far can we get? Very excitingly, there has been a Cambrian explosion of work that's looking at building alternative efficient architectures to the transformer. Again, this is a very interesting technical question, but also important for low resource, for open source, for cheaper models that can run on a broader range of compute. And not only is there this massive set of options we have, but there's also this clear picture in prior work that the models are not only using asymptotically faster primitives, but they're also matching the quality that transformers can offer us on language modeling. And so with that picture in mind, it's like, why don't we just plug these into all of our systems? But when we look at the leaderboards, when we look at what models people are training, it's very clear that transformers still dominate the landscape. And it might make sense. If we're changing our transformer model using something asymptotically cheaper, we might be giving something up in quality. And prior work doesn't really highlight what that is. So that's what we're going to dig through. So the rest of this talk will be as follows. In part one, let's understand the trade-offs between efficiency and quality and try to be a bit more principled about what that means. In part two, we have many, many efficient modeling candidates that have been proposed in prior work. Which of these are sort of at that Pareto frontier between quality and efficiency? And this requires us to think a little bit about how these architecture candidates map to the hardware. And finally, using our understanding from parts one and part two, let's work on expanding the Pareto frontier of these efficient models. By the end of the talk, I'm going to tell you about a model that I've released and a methodology that I've released that's allowed me to train 405 billion parameter attention-free model on an academic budget on 16 GPUs over 2 days. And for broad categories of tasks, be able to match original transformer models, full attention models at these scales, outperforming efforts to try to train these efficient models by major well-resourced organizations. How are we going to get here? We're going to build up piece by piece and work through the fundamentals. OK, so before we dive into part one, let me just give you a little bit of background on how language models work so we can appreciate the rest of the talk together. A language model is trained with a very simple recipe these days. Take a piece of text from a book from the internet. For instance, the cat in the hat is A. And the model is trained to assign a probability to what the next token is. So for instance, it might assign 0.2 to book or 0.0001 to frog. And we'll select the token that has the highest probability to continue the sequence, and then we'll repeat this process to generate more text. So the underlying computation that goes on in our model is trying to understand the meaning of some piece of text, like the cat in the hat, by computing interactions between individual elements of our sequence. And attention is one way to do this. Okay, so I mentioned attention has expensive compute requirements as we increase the length of text we're processing, expensive memory requirements. Let's go through a little bit of intuition and a little bit more math about what attention actually is. Depending on your familiarity with these concepts, you can appreciate the intuition or the math. So given our input of sequence length n and representation dimension d, we compute 3 transformations of that input, which are for historical reasons called queries, keys, and values, or q, k, and v, each again n by d. And then we compute this little equation over them. What's going on there? So first, we've multiplied our queries and our keys. And what this is roughly doing is allowing us to compute how relevant different tokens in our input sequence are to one another. For instance, this represents how relevant are the and cat in this sequence. And we use those values to take a weighted average of this v vector to get our output from attention. And we repeat this over many, many layers, and at the end of this process, have the model predict that the next token is the word is. So the compute requirements we can see here. In manifesting this matrix here, we have this n squared compute cost that we've incurred. And the representations that we compute here, as we cache them, consumes memory that grows with the sequence length as we process text. What makes the alternatives to attention and transformers faster? The main goal is going to be how far we can, the interesting question here is how far can we get with a constant amount of memory, independent of sequence length, and a subquadratic amount of compute in sequence length. And with this, we can get orders of magnitude faster or higher throughput compared to transformers. So while there are many, many approaches that people have proposed instead of attention, let me tell you about the 2 main categories that will help you appreciate the key ideas in this talk. The first way to become more efficient compared to attention is a category of architectures built on what is called linearized attention. So all that's changing here from what we saw before is we're going to throw away this exp and replace it by this feature map function phi that's going to be applied independently to q and independently to k. What this allows us to do is change the order of the matrix multiplications. So whereas before we had to multiply q and k due to this exp, incurring this compute requirement, here we have more flexibility. We can multiply our phi of k transpose with our values first. And by controlling sort of the properties of this feature map and this value of f, we have so much more flexibility in the amount of compute and memory that our architecture consumes when we run inference over our sequence. So if f is equal to n, this is the same as standard attention in complexity. But if f is a lot smaller, which it often is, we get a lot more compression and a lot better scaling there. The second core idea to build these efficient models is to go much farther away from attention and to use convolution operations to process over our sequence. A convolution is a standard operation in machine learning, signal processing, where you use some sort of convolution filter that governs how different tokens in our sequence get to interact with each other. Note here that the convolution filter that's used in a lot of these models is not going to vary as a function of the input u, whereas these queries, keys, and values are all functions of the input u. So a little bit of foreshadowing there. OK, now with that understanding of the categories of efficient models, why attention is inefficient, let's dive in. So just to pop up, models are trained on tens of trillions of tokens of data. And when we change our architecture from something like attention transformers to something entirely different, many, many things can break. How can we even start to make tractable progress on understanding the quality efficiency trade-offs? My approach is to start from large model behaviors and see what we observe at scale, distill the behaviors we observe at scale into formal synthetics or toy tasks that we can use to probe the behaviors of different architectures at small scales, and then use that simplification and formalization to facilitate theoretical analysis of how well different architectures solve important skills in language modeling. I know that's a lot, but let's dive in piece by piece. So because of this broad starting point, we don't know how to tractably understand quality efficiency trade-offs. let's start from a broad place here of let's look at what the models, different models predict as their next token. So here I've color-coded those for a popular efficient model candidate as well as transformers. Look here, the second section is all about Pixar. So both transformers and the efficient model predict Pixar incorrectly, denoted in red. The second time around, we can see that the transformer model is able to correctly remember that Pixar map to Fest and predict out Fest, whereas the efficient model still struggles. And this was a glaring failure mode that we observed when looking at this error analysis over many, many models over many tokens. And let me just contrast that to everything else, which is a non-recall token. So in order to correctly predict Disneyland Resort, the model would have needed to memorize this during training, as opposed to kind of using information seen in the context. This is just an anecdotal example, but using this simple proxy of dividing the tokens into two slices, it became clear that this explained 80 to 100% of the quality gap between efficient and transformer models. It is the core issue, this recall issue. So when we look at these two different slices, we can see that on these non-recall tokens like Disneyland Resort that are more memorization-oriented, popular efficient models and transformers perform identically in quality. On the other slice involving recall, especially when information is seen very rarely in the training data, there's a massive gap that occurs, and lower here is better. So why does prior work miss this? Why do they argue, okay, we match transformers everywhere? Well, when we take a look, these alternative models have made a huge splash. So 2,000 plus citations in a year, and on canonical standard benchmarks that the community has aligned on, they do indeed sort of match transformers in accuracy. But when we take a closer look at these models, they're all short context tasks, classification tasks, natural language understanding tasks that don't really implicate this recall behavior. In contrast, in my work to make progress here, I put together a new suite of canonical tasks called the Evaporate set of benchmarks that the community has now widely adopted to actually test the recall abilities. And so these are real tasks like information extraction, code generation, question answering. And on these tasks, we can see huge gaps occur between our efficient candidates and transformers. Okay. So we understand recall is a problem. Is it fundamental? Is it the only thing? Is it some arbitrary idea? What is the Pareto frontier of getting this recall quality? Or are we reserved to transformers? So to make progress here, we're going to take this observation, these empirical properties we saw at scale, and turn them into a simple synthetic that very shockingly can capture all the behaviors that we observe at large scales. So concretely, if I give you that same example, Pixar Fest, and then later Pixar Fest, I'm going to create a synthetic toy version of this, where now we have tokens that are these characters and numbers, so C maps to 8, A, 3, D, 1, and then as the model sees the sequence, later on it needs to remember what these mappings were. So A mapped to 3, C mapped to 8, just like standard next token prediction. And it's a very, very simple synthetic, but at the same time quite powerful. Let me tell you a little bit about it. So we're going to measure how well different models do on the synthetic. You can train on the synthetic in the order of 10 to 20 minutes, so it's quite cheap for rapid iteration. So when we train attention, we can see that with a massive amount of memory, due to all of its massive memory consumption, it can get 100% accuracy at this recall skill. Now, how do we be more efficient? Well, perhaps we can just throw away some of the representations for some of the tokens in our sequence and restrict to only sort of caching W of the overall N tokens. As we vary W, we have a linear trade-off between memory and recall. How can we do better than a linear trade-off? Well, there is a broad set of models that are built from those convolution primitives that I told you about in the background section. And while prior work had argued that, okay, these models match transformers in quality, we can see that on this trade-off space, they're actually suboptimal. And this maps to what we see on real models trained on real tasks in our suite. To provide intuition that I foreshadowed earlier, I don't want to overcomplicate it. It's basically an argument of something called input dependence, where transformers and attention, linear attention, get to decide how tokens interact in a sequence in a very flexible way governed by this input-dependent Q and K that are functions of the input U. While for convolutions, the filter that decides how tokens interact is not changing with U, yielding a much more rigid structure of how tokens get to interact. So building on some of these input dependence ideas, models have been able to expand the Pareto frontier for a fixed amount of memory. Think of, for different users, different compute constraints, get better quality than that naive sort of attention line that we had here. And again, that improvement maps to what we see on real models on real tasks, highlighting that this synthetic is indeed meaningful for behaviors that we see at large scales, despite being something you can train on in 10 minutes, 20 minutes. And a brief note on synthetics. These types of problems, synthetic formalizations, have been widely used in machine learning for many, many decades. What is important about the approach in my work is, one, to start from real-world observations and properties, and then build the synthetics to specifically have the properties that capture what is important on the real-world tasks. A lot of these models are designed without that feedback. And secondly, and more importantly, my work is looking at these scaling curves. So as we vary efficiency, what is the quality? These are point estimates for that same architecture H3 here that I'm showing is suboptimal, saying that for a specific instantiation of this model, they can get 100% accuracy on these recall-style tasks, but there's no notion of the scaling required or the efficiency with which they learn those important tasks. And so these are two important changes here. And finally, now that we have a formalization of this recall problem in the form of this meaningful synthetic, can we make progress in explaining which types of architectural choices can expand the Pareto frontier or struggle, and which are fundamental beyond this empirical work? So there are many diverse architectures out there. How can we systematically analyze them? Well, we could do it one by one and understand how efficiently do each of these solve recall. But instead, my work makes a unifying observation that while diverse on the face of it, these models are all built up of compositions of polynomial operations. So specifically, if I have my n by d input u to the model, each of those elements of that tensor is some input to a polynomial operation. So specifically in an element-wise multiplication, each element of the output tensor to this operation is going to be a degree 2 polynomial, taking in two input values, u sub 0 and v sub 0. For a convolution, where often one of the inputs is a fixed filter for a convolution filter, we have two inputs here. One is fixed, and this gives us a degree 1 polynomial. For linear attentions, we have three inputs of three functions of our input u, of three variables, and we get degree 3 polynomials. And so different ones of these architectures are composing these convolutions, element-wise multiplies, and so on in arbitrary ways. But this provides us a unifying observation that ultimately they're compositions of polynomial operations. What this allows us to do is to, instead of reasoning about this messy landscape of architectures, reason about well-known theoretical tools. Specifically, an object called an arithmetic circuit, or directed acyclic graph, where the nodes are either computing multiplications or additions, is the canonical way of measuring the complexity of a polynomial. So an arithmetic circuit, this well-known theoretical tool, computes polynomials as a function of its input, and I'm arguing so do our efficient models. They compute polynomials in the input. And so what this has allowed us to do is, in my work, we propose sort of this canonical efficient model with different convolution, Hadamard product operations in it, and prove that within tight polylog factors, it's equivalent to general arithmetic circuits. Why is this important? What it allows us to do is argue that this architecture can simulate any of the architectures in this messy landscape. So when we want to theoretically analyze how well do different types of architectures solve recall, we can analyze how well this base conv architecture solves recall as a proxy. Let's see this in work a little bit. So first, we can say that any base conv model that uses input-independent convolution filters, which I've told you a little bit about, and Hadamard products in any composition of them, will require a larger number of layers to solve that recall synthetic compared to what transformers can use to solve the synthetic. And this matches what we saw empirically on synthetic as well as real language model data. Secondly, we can say that if these filters are input dependent, building on this input dependence intuition I've given you, we can recover the number of layers that transformer used to solve the recall synthetic. Again, mapping what we saw on the trends in real data and synthetic data. But ultimately, there's no free lunch, and I hope this is very intuitive to you. If I'm trying to use a small amount of memory to process large sequences of data, there's a fundamental information bottleneck there, which we can talk about using communication complexity theory. So across all of these models, there's a fundamental trade-off. OK, so we understand these key ingredients, recall, input dependence, and the fundamental memory trade-off. The tools that I've talked about here, the analysis tools, the synthetics, and so on, have become the de facto tools in this line of work on efficient models. So if you pick up any of these papers, they're going to use these plots and tools that we've built out here, really helping expand our ability to have improved efficient models.
Just a couple of questions. One was regarding the convolution structure at each layer. Is it the same convolution structure at each layer, or do you assume that there could be different convolution structures at different layers? Because I can imagine that I think what you're trying to capture is being able to have information flow through layers as opposed to kind of within the same layer.
Great question. OK, so as we train this model, every single layer is going to have unique trained weights that are the convolution weights. And if we imagine our n by d input tensor, we run a unique one-dimensional convolution on every one of the d dimensions. So these can, in essence, shift the sequence and allow different sorts of interaction patterns. But what you should think about is, in the worst case, O of n different interaction distances are required. So O of n different convolutions are required. I know that's not the same as the layers argument, but you can kind of see where this rigidity requires us, and lack of input dependence requires us to have the scaling with sequence length.
So it's very interesting. So another, I guess, the trade-off that you seem to be getting at is that I could invest in a few more extra layers so that I can capture these long-term dependencies between tokens.
Yeah, and also the conceptual point here is that a lot of this work has said, OK, a convolution can process text subquadratically, but the conceptual shift is we should be thinking about how efficiently these architectures can solve meaningful tasks like recall, as opposed to just how fast can they process sequences. OK. So with that in mind, now let's measure where we're at on this Pareto frontier between in-context recall and efficiency with different models. And I know that we've talked a lot about modeling, and we'll get back to that in part 3, but it's really important for us to understand the systems pieces as a first precursor to getting back to how we can expand the Pareto frontier. So mapping algorithms, AI algorithms to the hardware has been a key bottleneck in machine learning. So even for the workhorse transformers, which have been around for a decade at this point, it took 7 years to get high quality, high utilization kernels on modern GPU hardware. And when NVIDIA's next generation of hardware came out, the H100, the performance of these older kernels degraded by 47%, and it took 2 years from the release of this new GPU hardware to recover that performance with what was called flash attention 3. So it's been hard to support transformers, what everybody is using, let alone these efficient exotic architectures. And when we actually look at these efficient architectures, and where we were previously looking at memory consumption and in-context recall, now let's look at their wall clock time to process sequences and in-context recall. We can see that for pretty reasonable sequence lengths and batch sizes, they're not actually providing higher quality for a fixed amount of wall clock time compared to what transformers and attention can offer us in blue here. OK, there's a lot of work to do to make these efficient architectures actually just co-designed with the hardware and not just designed for quality and theoretical asymptotics. There are 2 reasons why mapping algorithms to hardware has been hard. The first is that some of the architectural choices fundamentally are incompatible with what the hardware prefers in a category of ideas here. But the one I'm going to focus more on is that the programming tools that we have to write our hardware-efficient code are rather difficult to work with for the AI audience. So AI people write their algorithms in Python, something like PyTorch, TensorFlow, JAX. And we love to think in Python. And so there are these Python tools like PyTorch, which will call to well-optimized kernels for popular operations in machine learning under the hood. But for the flexible ideas and architectures I'm talking about, they're entirely insufficient. There are Pythonic tools like something called Triton released by OpenAI that you can use to actually, with a Python style, go and control how programs get mapped to the GPU hardware. But by providing simplicity, they sacrifice our ability to get peak performance out of the hardware pretty significantly. On the other end of the spectrum, there's very low-level libraries like CUDA and Cutlass provided by NVIDIA, so it's very vendor-specific in contrast to these, but widely used, allow you to get all the performance and squeeze all the juice out of the hardware. But AI people don't think in terms of deeply nested C++ libraries, and it has been very difficult for us to map algorithms to hardware, as I've pointed out. OK, so how do we make progress here, and what was my contribution here? So let's take a look at what an NVIDIA H100 hardware looks like. These little green dots are what are doing compute. They have some memory within them, but very, very little memory that is very fast to access because it's so close to the compute. Farther away, we have these 4 little rectangles here called an L2 cache. You need to transfer data a little bit farther away for the compute units to access data there, so it takes a little bit longer. And then farther away from the compute units, you have even more memory available, and we have a lot of space for just managing the currents. And so this is basically what a GPU looks like: compute and memory. When you do compute, you need to do it over some data, some memory. OK, zooming into one of those little green dots over there, this is what's going on under the hood. There are different types of units for doing integer, floating point, double precision computation. There are different units for doing loads and stores of data, for doing special functional unit for doing mathematical operations, and something called a tensor core, which is specialized to matrix multiplication. So this is what's going on in one of these green dots. So different types of circuitry specialized to different types of parts of our AI kernel. There's one rule in hardware-aware AI on modern hardware, which is to keep that tensor core piece fed, because it's 16 times faster compute than the next compute available on the GPU. The hard part of hardware-aware AI is everything that's required to make that possible. So you don't have enough fast memory in order to store the massive data matrices and models that we're working with in AI. So you need to think about how to move data across different parts of this hierarchy. There are non-matrix multiply operations that are required, and so on. OK, so here I'm going to tell you a little bit about how to think about a simplified model of GPU parallelism and how I built a set of programming abstractions to make it easier for AI researchers to map their algorithms to hardware. OK, so a basic unit of execution on a GPU is a thread. And GPUs have tens of thousands of threads that are working together to do our AI workload. And these threads work together in groups. They're tightly coupled. They run the same sort of instructions together. And what's very difficult is for AI researchers, to think about how to map different elements of data that we might be working with when we're loading and storing data to which threads actually own these different pieces of data. And you might think, oh, why not just have thread 1 own element 1, thread 2 own element 2, and so on in our matrix? That's not how it works. It's a lot more complicated. You need to think about these messy pictures of how logical data maps to physical thread ownership. And it has very important implications for the speed of our program. Secondly, within the program that we're operating, we're going to have different groups of these warps that are these tightly connected sets of threads working together to perform some of our computation. What's very important is how to set the number of warps that are going to be working together. And what's important here is that when I showed you this picture of what's going on in the compute, different ones of these warps, different ones of these threads can be working on different parts of these circuitries at the same time, something called occupancy. And what's very fundamental is to as you have more threads working together on these processors, you can have more of these different circuitry occupied together, which is very nice. It reduces your latency of your program. But at the same time, these threads need to fight over precious resources, like the limited amount of memory that we have on the GPU. And finally, it takes time to launch different kernels and to launch these groups of blocks that are going to be working together, which all have important costs associated with them. And so there are many factors to consider when programming GPU hardware, and I hope that gave you a little teaser. So what I proposed in my work is a library called Thunderkittens, where it's using a lot less code in terms of the library side. Obviously, this is an imperfect proxy compared to sort of comparable use case libraries here. And I'll argue is a lot more aligned to what AI researchers' experience looks like when programming. So the first basic data structure in Thunderkittens is a basic 16 by 16 tile that warps own together. And this is designed to maximize compatibility with those tensor cores or special matrix multiply units we want to be occupying. And we automatically pick the layouts, that mapping of data to physical threads, for the user at the library level so that they don't need to worry about it. So actually using these tiles is a lot like using a tensor in PyTorch to the programmer. Once you start thinking in terms of these tiles, you'll realize you want to do operations on them, like matrix multiply or exp or add or so on. And so we have library functions that are just templated functions over these tiles that are drawn from what's used in PyTorch and NumPy in inspiration, highlighting the Pythonic philosophy of the Thunderkittens approach. And finally, we have at the block level, at the thread block level, when I mentioned you want different groups of threads to be doing different types of work at the same time and manage their occupancy contentions, we have a general single kernel template that's provided in the library that helps the user automatically manage how different subsets of our threads are going to be partitioning different types of work involved in our AI kernel. And so synchronization between these different groups of threads is managed by the library on the back end. And all the user needs to do is kind of specify what types of data needs to be loaded, what types of compute need to be done on these tiles, and orchestration around that is done by the kernel template at the library level. And the simplified interface in Thunderkittens via this unified kernel template makes it easy for users to tune properties of their kernel or their GPU program that are required for sort of different workload properties. So in particular, when I mentioned there's this trade-off between the number of workers or threads doing, kind of executing together at the same time or occupancy, and this contention over limited memory and limited resources, it becomes very easy to tune these parameters with just a couple of seconds per setting using Thunderkittens and just modulating like sort of a single number in the kernel template. And this template helps expand the frontier of efficiency we can get over a simple warp parallel type of kernel that doesn't have this sort of producer-consumer, for those familiar with that concept, kernel template. And finally, we use a persistent grid kernel to kind of hide the cost and the time required to launch these different thread blocks and schedule them on the GPU. So that's kind of a rough overview of Thunderkittens there. How have we been able to use this? So across a broad set of AI workloads, across different hardware platforms and different vendors, so NVIDIA 4090, NVIDIA H100, even Apple hardware, Revos, which is not pictured here, I'm going to show you the lines of code of Thunderkittens used compared to baselines. So for the very low-level libraries like Cutlass, CUDA, here we can see we're using roughly a tenth of the number of lines of code while maintaining sort of comparable performance on hardware utilization. Compared to the simplified libraries like Triton, we're able to sort of have a comparable amount of lines of code, but get pretty sizable speed-ups in terms of how fast we can run these algorithms on the hardware. And it's important to note here that some of these baselines are the subject of entire research papers of people dedicating their time to go and optimize this operation. But by kind of building at the library level, building out these abstractions, we've been able to tackle a broad set of algorithms. And again, it's not just vendor specific. A co-author on this undergrad is going to jump trading, getting paid millions of dollars per year to write Thunderkittens kernels. So it's been quite interesting to see the impact of this work. So within less than a year since its release, 2.2K GitHub stars, it's been used in quite a few research papers by different universities. Here's a testimonial from someone I've never met before. It's also being used in industry, jump trading, Together AI, and Cruise. And most importantly, I'll point out, so we released this publicly for the first time in May of 2024. This entire past GTC was about Pythonic waves of Cutlass and new types of Python DSL. So I think philosophically, it's had a lot of impact in the way we wanted of making mapping AI algorithms to hardware much easier. OK, yeah, go.
Can you say a little bit about the speed up over Triton and just like where that's coming from?
Yeah, so specifically it comes from being able to manage what is maintained in the register memory very precisely and carefully. And then also it's hard to implement these patterns like producer-consumer or worker specialization with Triton because it doesn't expose sort of fine-grained synchronization primitives. OK, so how do we expand the Pareto frontier beyond what we're seeing here? OK, so there's going to be a really simple insight. And then I'm going to tell you about simple primitives that we can use. And then finally, we're going to look at some big models at large scales. So simple observation is that recall, this whole issue we've been after, is really required more heavily between tokens that are close to each other in real language data. So if we take a massive corpus of popular language data and measure how frequently, how far apart PixarFest and PixarFest, or these sort of bigrams are in the data, it follows this power law distribution, where often it's required between nearby tokens and less so between far apart tokens. OK, let's just use that. Let's very precisely model the interactions between local tokens and cheaply approximate the interactions between far apart tokens. So how do we do that in a simple way? Well, first, we are going to take an idea we've already seen of using attention, but only within some local region of maintaining sort of the last running set of W tokens as we process text. And this is called sliding window attention. It's going to help us precisely use attention to compute local interactions. And secondly, we're going to use another idea we've already seen of linear attention, where we have, again, to remind you, instead of X peer, we have some feature maps that gave us that flexibility in the order of the matrix multiplications and in choosing a feature map to balance quality and cost. And specifically, combining these two ideas, and I'll tell you a little bit about what's more interesting there, but combining these two ideas, we've been able to expand the Pareto frontier between sort of memory use and quality compared to those popular architectures like Mamba that I mentioned earlier. And so again, what we've done here is combine linear attention that works at long ranges, combine attention that works very locally at short ranges but precisely, and put them together in what's called the based architecture. And what's also exciting about that is that it's so similar to transformers and attention. This workhorse that we've spent 168,000 citations studying very deeply, as opposed to making these strong deviations from the transformer architecture. OK, now let's dive into one piece of why this architecture works well. A big choice about this is how to pick that choice of the feature map function phi. And linear attention has been proposed and around for a while. And there are many different proposals for how to choose that feature map function phi. The specific approach that we used is able to be very, very hardware efficient while retaining good quality. So specifically in based, we propose to use a Taylor polynomial approximation of that exponential function that's occurring in the standard softmax attention, which I'll tell you a little bit about. And by choosing that Taylor polynomial in orange here, we're able to, for roughly decent model parameter count, decent working memory size, get pretty good quality compared to alternative choices of that feature map function phi. Specifically, remember that a Taylor approximation of x, exp of x, is going to be 1 plus x squared over 2 factorial, and so on to infinity. This is the exp that's in our standard softmax attention. Turning this into a feature map, we get 1 q outer product q over 2, and same with k's, We multiply them together and get an approximation for our exp of qk transpose in standard attention. Infinite terms are required to exactly compute x, but that would be very expensive because the size of this tensor grows very rapidly. We find roughly using a second-order Taylor polynomial balances quality and efficiency. And for those of you who think about hardware a little bit, we can reuse the same Q in multiple terms of our Taylor polynomial once we've loaded this Q data into fast memory on our GPU and compute these different terms. And so it allows us to basically use tensor cores in a way Mamba didn't, have lower sort of data movement overheads while still being able to compute relatively large state sizes or memory sizes for our linear attention model. And so kind of using this and building from the hardware up, we can see that on that wall clock versus recall trade-off space, we've been able to use 8 times the amount of memory that Mamba uses while still running at 5x the hardware utilization, again, by building from the hardware up. OK, and finally, yeah.
I'm just curious, so typically, how many terms of the Taylor series expansion do you end up using?
Roughly 2. Yeah.
Roughly 2.
Yeah. But we have played with other ones that I can talk about offline. OK, so training and evaluating some of these ideas on an academic budget is very hard, but I'll tell you that there's a lot of exciting modeling work to do on an academic budget. So for 405 billion parameter llama model, it takes 16,000 GPUs, 54 days, 15 trillion tokens, and for some sequence length and batch size, 2.2 terabytes of memory are required for that cache that I'm talking about for attention. So a lot of work has tried at the 8 billion parameter scale to train alternative models that have been proposed from scratch, efficient models, non-transformer models, but really sacrifice their recall performance. My work has been able to close a lot of these gaps, and with combining with 50% of attention, retain the overall quality on types of tasks that require recall. Next, the way that we do this is obviously not by training from scratch on an academic budget, but through methodologies I've proposed of taking these open source nice artifacts that we have and turning them into these based attention style models using a style of model distillation or model conversion technique, which I won't tell you about. But I think this is a really exciting path to evaluating a lot of these architecture and modeling ideas on an academic budget. And so doing this is how we could close a lot of the gaps. But you might say, oh, the 2 things are changing at once. You're using based, but you're also doing this model conversion. So compared to other works that have used model conversion to try to test out these efficient architecture ideas, despite them using 500 to 2,000 times more training data than what we use for based, we're still able to get much better quality out of the architectures that we've put out. And finally, we've scaled to 50 times larger than prior work, which is all at the 8 billion parameter scale, doing this for the first time at 405 billion parameters. And these are models you can reproduce yourself and try out yourself on Hugging Face. And when you use these alternative models for these classes of tasks, you can get roughly 2.2 terabytes to 33 gigabytes of memory use. It's not perfect. There's still lots of work to do, but we've made a lot of progress in this line of work. And based has really changed the landscape of these efficient architectures. So since its release in December 2023, a lot of architectures have been designed around these similar concepts of using linear attention with large state sizes and these local computations like the sliding window attention. So just to summarize, simple tools like synthetics were shockingly powerful to help us break down this intractable problem of analyzing language models and architectures and make progress. We want to build architectures from the hardware up, pipette the bits as fast as possible. There are many ways to get quality, but that's the path we'd like. And finally, with open source being here to stay and all this investment by companies, I think it offers us really exciting potential modeling work to do on an academic budget. Just to close out, a lot of my work and choice to work on these efficient models has been motivated by the fact that I really want, a key promise of AI is our ability to support machine learning and assist users on their personal tasks that they care about, which we've made very little progress on. But I think by having these efficient modeling techniques, we can keep models local and data local and start to make progress towards these goals. To elaborate a little bit, so suppose we want to assist domain experts on complex and niche tasks. Suppose I want a model to generate some sort of CUDA kernel. Maybe I want it to use thunderkittens, which are open-ended monolithic models out in the world, are not trained on this niche library that I've proposed. How do you inject them and get them to use the sort of abstractions that we care about? And finally, we're not just having models sort of take one input and propose one output anymore, but in a current paradigm called like test time compute, we're having our models go and explore many, many different possible solutions to that input problem we provided, potentially interacting with code execution terminals, profilers, and different tools that result in an abundance of context that we need to process with our models in order to make sense of. And so all of this process requires massive, massive amounts of context length that's generated, different problems here in order to abstract, to use the abstractions that we care about in our individual personal workflows. And I think as a whole, you can kind of see different places where we've really only focused on one specific, two specific trade-off points in a massive landscape of resource utilization of constant memory or linear memory. But resource utilization should really be input dependent as we're tackling these more difficult tasks and reasoning heavy tasks. And secondly, we've really focused a lot on vision and images, but transformers really struggle to model numerical data and floating point data, which I've shown in some of my work as well. We have very little progress on being able to model sequences at multiple scales and resolutions efficiently. And while transformers seem well equipped to modeling discrete data like tokens, really struggle to precisely model floating point data, kind of provably from first principles. And it's interesting as we sort of start to tackle some of these tasks, how we can devise models that are appropriate for both. And finally, I'm particularly interested in pushing on this line of work on hardware programming abstractions to facilitate exploration and fast iteration on AI algorithms. So while thunderkittens was focused on writing individual GPU programs or kernels, we have a lot of inflexibility in our tools to program multiple GPU and multi-node systems. So NVIDIA has a tool called Nickel, for those familiar, which is rather rigid in the control primitives it offers us. As we want to have systems that can, as I mentioned earlier, operate with code execution terminals, with profiling tools and multiple components, databases, web search in the loop, with very different operational intensities, this introduces interesting systems problems as well as to how to orchestrate all of this. And finally, if we have, towards this personalization front, sort of models on our local compute that are working on our local data, which are not very high quality, and we have these powerful models in the cloud, how can we think about the APIs and the interaction patterns between these two resources that we have to enforce better privacy personalization on edge compute? So with that, I'll wrap up. We've really focused on a specific recipe in AI, and I'm really excited about the potential paths forward that can offer us far cheaper approaches there. And I think that, again, AI and systems is really going to be at the forefront of this push forward. Thank you, and I'll take any remaining questions.
Yeah, we have time for a few questions.
What is a good number for academic budget?
It's a great question. So the work that I'm talking about there was done on 16 H100 GPUs on 2 days. So I'd say, depends on the lab, obviously, but roughly 1 to 4 nodes, I'd say, is in the scope of what you could access. And for the 8 billion parameter experiments we did, that was on a single H100 GPU, so not even a full node. And so I'm talking, within 2 weeks of training, within 1 to 4 nodes of GPUs. Yeah.
Go ahead.
Can you explain why associative recall was so important for the MLU benchmark?
So for those, so the question was, why is associative recall important for the MMLU benchmark? So MMLU, for those not familiar with the space, is a very, very standard benchmark that industry cares a lot about, academics care a lot about for various reasons when benchmarking the quality of language models. And in the structure, it's basically multiple choice from science, from math, from geography, and so on, where you have some sort of input and question and multiple choice responses. Like A is 5, B is 10, maybe if it's a math question. And typically, 5-shot MMLU is something where we provide sort of 5 in-context examples or 5 question and multiple choice pairs along with their answer, and then finally have the model go and answer the final question. Being able to solve the question, say if it's this math question, 1 + 1 = what, and then solve that question and map it to the multiple choice offerings, like A is 3, B is 20, C is 1,000, and so on, requires doing recall association in order to do that mapping. So that's one place. And then also kind of picking out the specific part of the 5 in-context examples that's relevant to answer this question requires recall as well. Yeah.
Quick follow-up. So you said that when you were using based attention, you also added 50% attention as like a second version. What did that mean?
Yeah, so there, the Llama 405 billion parameter model, that was at 8 billion parameters, but say 405 is 126 layers of attention. So that would entail retaining 64 attention layers and 64 non-attention layers. And at the 8 billion parameter scale, that's what we did. Yeah.
So that basically comes at
Cost of memory, yeah.
Got it,
So,
cost of-
so in that chart, we kind of showed the memory requirement for both pure subquadratic as well as the hybrid model. And these hybrid models are being, kind of incorporated in a lot of models people are putting out these days.
How should they be distributed in terms of, should they come at the end? Should they be interspersed throughout the transformer?
Yeah,
architecture?
so people have different, I wouldn't say it's like fully characterized. Part of it is like, there's not an exact theoretical argument for one or the other, but typically people put them at the end of the architectural stack where you want to be able to do like sort of global condensation of the individual bits of ideas that you've built up by modeling across the earlier layers. Yeah.
Okay.
Do you think the efficient architecture you're proposing or future efficient architecture can learn data more efficiently? Because I think you saw the result that not only the architecture is more efficient, but you can only train on much less data. What is your opinion?
Yeah, so in a variety of respects, think we can learn more efficiently. So on that front of the converting these 405 billion parameter models from attention to based attention, we picked arbitrary data to do the distillation process, just something called red pajama or alpaca or one of these canonical benchmarks. The actual distillation method goes as follows. So at specific layer L, we compute our standard attention with the original MetaLlama model, and then we compute our based attention y hat, and we minimize the mean squared error at every single layer on some input data. And then we kind of end-to-end stitch together these layers using some lightweight end-to-end LoRa say next token prediction. So when you pick that distillation data in that first step, mean squared error, you're trying to get the based attention to be a high fidelity approximation for the original attention. And so you want basically data that covers the spectrum of the original attention map. So if all my data is of a very particular form, I'm not going to get good coverage, and my new model is not going to be very good. And so when we picked arbitrary data, it was a fine thing for like the first set of paper here and projects here, but like an interesting direction for future work is like, can you actually use the spectral properties of these individual layers and pick data out in a way that will give you good coverage and a better approximation? Yeah.
So one thing I'm trying to understand is, how do I contextualize the techniques you're proposing in your work compared to other models like DeepSeek, which also claim to have less training cost and potentially less data as well? Is there an overlap in terms of techniques? What is the trade-offs? What is what's happening there?
Great question. It's pretty complementary. So DeepSeek made a lot of progress by using sort of lower precision computation for certain parts of their training, mixture of experts for that MLP bit, which we didn't talk at all about in this talk, and like implementing it in a nice way. There's also something called native sparse attention, which is like a version of efficient architecture they recently put out. So the MLP bits and the precision bits are complementary to this. The multi-head latent attention is actually going to cut your KV cache in half already because you don't need to independently store keys and values. And so that's a pretty cool technique that they put out, but it'll still have the same sort of asymptotic scaling there. So there are a variety of techniques: quantization, KV cache compression, these subquadratic architectures. And again, like I think there are many ways to get to quality, but it's really interesting to kind of consider each of these points in each of these recipes. And I think like generally the types of throughput improvements we're going after with the subquadratic models are much more drastic than what the typical KV cache compression paper kind of reports at the end there.
And they are orthogonal in the sense that you could combine some of those techniques.
Mm-hmm.
Go ahead.
Yeah. So at the beginning of the talk, you were mentioning the subquadratic architectures, and you were mentioning how the arithmetic circuits for them were lower degree. Can you repeat again, like why that's an important point? And second, what's the degree of the polynomial of the arithmetic circuit for standard attention?
For standard attention, it's not a polynomial because you have a softmax there, which is a non-polynomial operation. For linear attention with a polynomial feature map, it was the degree 3 polynomial there. So what's interesting to consider is if I have some model that across the layers is computing some polynomial, if I am doing this associative recall task, let's say, of A maps to 1, C maps to 8, and so on, and I want the model to remember these mappings, the type of setup that one could look at is to say, suppose we have Alice and Bob, a standard like communication complexity setup, and Alice has all of the information about A map to 1 and D map to 8 and C map to 4 and so on, and fills in coefficients for some of the polynomial of the circuit to compute the answer of the associative recall task, and then wants to pass over this information to Bob, who then has to go and remember what did A map to, what did D map to, and so on. And so there we can sort of bound the communication required between Alice and Bob in order to compute the answer out, and that's how we were able to get the lower bound there. And so the framework, depending on is it an upper bound question, is it a lower bound question, and so on, has like different styles of how we analyzed it, but this arithmetic circuit and polynomial kind of unification allowed us to study different aspects of the question.
Okay, I think let's wrap it up. Thanks very much. That was a fantastic talk.
Thank you.